Hey guys, so today we're going to be looking at the solutions for the homework problems. So the first one says the shelf life of a particular dairy product is normally distributed with a mean of 12 days and a standard deviation of 3 days. So we've got our mean, our standard deviation. And it is a normal distribution, so we're going to go ahead and read the part A. 1% lasts between 9 and 15 days. So our mean is 12. And we want 9 and 15 days. We want the percent of the products that last between these days. So we're going to calculate to the right of 9, to the right of 15, and subtract them. I'll start by using the chart. So to do that, we're going to convert 9 and 15 using our formula. So we're going to use this formula to convert 9 and 15 to standard scores. So for 9, standard deviation is 3. 9 minus 12 is negative 3, divided by 3 is negative 1. For 15, use different color. That's 15 minus 12 over 3, which is a positive 1. So now we're going to look up the negative 1 and 1 on our standard normal distribution chart. Negative 1 is right here. Let's zoom in. Gives us a probability of 0.1587. Now again, these charts give us the area to the left, and we need the area to the right. I'm going to take this 0.1587 I'll put it here. So that's the area to the left here. So this is that area. And we want the area to the right. So again, total area under the curve is 1. Rule of complements will get us probability of being to the right of that z-score. That gives us 0.8413. Okay. For the 15, we're going to look at the positive z-scores. 0.8413. Now if I do 1 minus 0.8413, that's just going to give me this number right here, 0.1587. So we're now going to subtract these two to see what our total probability is. It'll be a decimal, and we'll convert it to a percent after that. 0.8413. Again, this 0.1587 is a probability right here in this region. So the 8413 is everything to the right of this z-score. The 0.1587 is everything to the right of this z-score. So if we subtract them, that'll give us what's between those two z-scores. subtract 0.1587, and that'll give us 0.6826. So probably is 0.6826. Convert that to a percentage. It's going to be 68.26%. That's the part A. Now with the calculator, start with Casio. We are in a normal distribution. Again, pretty much never going to use the PDF for normal distribution. We're on cumulative, number 2. Lower limit, 9. Upper limit, 15. Standard deviation was 3. And the mean was 12. And 0.6827 in this case with the calculator. Again, if we're using the charts, they only go to 4 decimal places. So there is going to be some rounding error, and you'll get a slightly different answer from the chart than you would from a piece of technology. And that's okay. Sorry. Now the TI, same process we did yesterday. Second FARS, null CDF. Our lower bound was 9, upper bound 15. A mean of 12, and a standard deviation of 3. And again, if you're using a TID3, it'll just pop up with null CDF, and you have to type these values in with commas. Hit the enter button, and you get the same thing, 0.6827. Okay. For part B, process is exactly the same, so I'll just go ahead and use the technology. So we're looking for between 12 and 15. Well, where's 12 at? It's right here. That's our mean. So, excuse me. Let me just pause this. Okay, so it's just a package. So since it's at 12, we know for sure that 50% lies on either side of that line because 12 is our mean. So we can save ourselves some time there. If you do standardize it, let's see what happens. 12 minus 12 is 0. Divided by, doesn't matter, it's still going to be 0. And if we look up 0 on the standard normal distribution chart, there it is, 0.5. So anytime you have your mean, it's just going to be a probability of 0.5 on either side of it. So what we really need is to the right of 15. If we look at the chart, we have to convert it. 15 we already found was 1. Since we already have the numbers here, might as well just do it by hand. So that was 0.8413, which gave us to the right this probability right here of 0.1587. So 0.5 minus this 0.1587. Here's 0.3413. And that would be 34.13%. Real quick, let's see what the calculator tells us about that. lower bound of 12, upper bound of 15, and all that's the same. 0.3413, same thing. Casio, lower bound is 12, mean is 15, same. 0.3413. So we had most of the numbers from part A already. That wasn't too terrible to calculate. Now part C asks last 6 days or less. So right here's our 12. Here's 6, it's the left of the mean. So for the chart, we're definitely going to need to convert that. 6 minus 12 over 3. That's negative 6 over 3 is negative 2. So we're going to look up a negative 2 right here, 0.0228. So that would give us the probability is 0.0228. That's to the left. This is this area here. And it's asking for less than, that is actually what we want. So we're done, found our answer. Casio, lower bound is negative infinity. Upper bound is 6. Mean standard deviation haven't changed. 0.02275, which does round to 0.0228. TI, lower bound, negative infinity, negative 99, 6, and those are not changed. Excuse me. So either way we do it, we get the same result. That's again for percentage. So that would be 2.28%. Last one on number 1. Mean hasn't moved 15 days or more. So here's 15 or more. So we've actually already have that answer. If we look back on part A, we calculated the area to the right of 15 to be 0.1587, right there. Okay, my mom's on the way. So this we already calculated is 0.1587. Now we can check that with the calculators. Lower bound is 15. Upper bound is 1 times 10 to the 99. And we get 0.1587. TI, lower bound 15, E99 positive, and same thing. So 15.87%. For number 2. On a recent math test, the mean score was 75 and the standard deviation was 5. Mike scored a 93. What is test score be considered an outlier? What is test score for normally distributed? Explain. This whole explain thing is what I was really looking for on this one. We never formally decided what would be considered an outlier for a normal distribution. But let's think about what we learned about z-scores and probabilities. Well, what is a z-score? How many standard distributions away from the mean we are. So if we're at 75 for the mean, and this guy's a 93. Well, if you remember back in the binomial distribution, we said if this right tail was less than 5%, we'd consider an outlier. So that's one way you might think about it. The range rule of thumb, we also say if it's with that with if it's within 2 standard deviations, I mean it's usual. Anything outside of that's unusual. Let's just look at the z-score, see what happens. So I'm going to convert it. It's going to be 93 minus 75 over, and the standard deviation is 5. 18 over 5, and that's 3 and 3/5, so 3.6. So that's a pretty large standard deviation there. It's over 3.5 standard deviations away from the mean. So if I were looking at this, I'd like, yeah, that's probably an outlier. Let's see what the probability is of it being 93 or greater. So let's go to the chart. We have 3.6 positive. Okay, 3.5 and up has 0.9999. Yeah, okay. So all of this stuff back here is 0.9999. Yeah, so that makes this piece right here 1 minus 0.9999, which is 0.0001. And that's for anything 3.5 or greater. So yeah, you can definitely consider this guy an outlier. So something to detect. Since Mike's z-score was 3.6, we can consider this test to be an outlier. Or, since the probability of earning test score of 93 or greater is 0.0001, we will consider Ike's test to be an outlier. Something to that effect. So the main thing is talk about the z-score and or talk about the probability. If you look at these two values, you can definitely say that this guy's out there. All right. Oreo factory, the mean mass of P is 40 grams. For quality control standard deviation is 2 grams. Can't have heavy cookies. If 10,000 cookies were produced, how many cookies are within 2 grams of the mean? So that's 1 standard deviation. So here's the mean, 40 grams, and we want within 2 grams. So that would be 38 to 42. But it's not asking for probability. It's asking how many. So if we think, what could that mean? We're given a number of cookies, and we're asked how many are within that 2 grams of the mean. Well, if we calculate the probability of being within 2 grams of the mean, and multiply that by our number of cookies, then we'll have how many cookies should be between 38 and 42 grams. Let's do that. So using the chart, you need to convert them to z-scores. Oh, we already did them. It's 2 grams, and the deviation is 2 grams. So without doing any work, 2 divided by 2 is 1, and this is negative. 2 divided by 2 is 1, that's positive. So it's negative 1 to 1. And we already looked at those values in the first problem, -1 and 1. And we found that exact percent right here for number 1. It's the same exact problem as number 1. So we have 68.26%. I'm just going to copy all this work over. So once you get it standardized, it doesn't matter what the original values were. We have a z-score of -1, we have a z-score of -1. We have a z-score of 1, we have a z-score of 1. So all of this is going to be the same. So really I didn't need, this section just needed that. So we can use a calculator and check. Let's see. Lower bound is 38. Upper bound is 42. Standard deviation of 2 this time, and a mean of 40. So we get 68.27%. Again, we use the chart for this one, so it's slightly off. Let's see. 10,000 cookies, 68.26%. Multiply those together. One, two, that's 4 zeros, that's for me, so right there. 6, 8, 2, 6. 6,826 cookies, 6,827 if you use a calculator. So if we go take that answer times 10,000, it'll be 6,826.9 or 6,827. Okay, cookies are rejected if they weigh more than 44 grams or less than 36. So yeah, they don't want to throw away 3,200 cookies. That's just ridiculous. But let's see how many cookies will be thrown away if we are out of this range here. So, hey, I bet you that's 2 standard deviations away. That's what it looks like. Let's see those z-scores. So 44 minus 40 over 2. Sure enough, that's a 2. And 36 minus 40 over 2 is -2. Did we do that one yet? We did -2. So we know, we can just do it again. So between -2 and 2, I'll just use the calculator for time's sake. 3, number 2. Lower bound was 36. Upper bound was 44. Standard deviation of 2. Mean of 40. 95.45. So the probability for part B, this is part A, part B, is 0.9545. So this would be between, I didn't draw my chart, did I? Let me copy that. So here's a 40. And what we just found was the probability of being between 36 and 44. So we found this probability. But it asks how many cookies would you expect to be rejected. So we actually need this probability. All we're going to do is rule of confidence. And that's going to be 455. 0.0455. Multiply that by 10,000 and you get 455 cookies. So they're going to throw away 455 cookies out of 10,000 just because they didn't weigh the right amount. Okay, so let's go to the next one. Tires this time. Let's see, I believe, this one. So 68% of all tires will have a life between what and what? So this one we're looking for z-scores. Given the mean, standard deviation. Mean 30,000. And we're looking for these z-scores here. So this part right here, we know to be 68%. Okay, so we're going to have to think a little bit. What we really want is these z-scores. Well, that means we need the area to the left of each of these z-scores. So I can get how much is in each one of these pieces here. And we know it's going to be even. So let's see. That's 32%. If we split that in half, we're going to get 16% on either side. So the main thing I want is right here. That's 0.16. So what I'm going to do is I'm going to look up 0.16 on my chart because we have the area to the left is z-score. Let's call it z1, z2 is 0.16. Let's see. Let me go to the negatives. Here's 13. Okay. 14. Oh, there it is. 0.16. We have two values for that. Oh, wait. What am I looking for? 0.16, not 0.016. 0.1. Okay, getting close here. There we go. So we have 0.1611 and 0.1587. So this is 13 10,000ths away. This is 11 10,000ths away. We're going to use this one. Negative 0.99. So now to get this Z2, this is 68%, that's 16%, so altogether that's 84%. 68 plus 16 is 84. So I'm going to look up the 84 in the chart. It's going to be positive. I'm going to look at 0.99, see what that is. Oh, hey, look. 0.99 is also 11 10,000ths away. And this next value up, 1 is 13 10,000. So 0.99 is closer. So these are our z-scores, and we're going to use the same formula we've been using. Here it is. This formula right here, we're just going to convert it to solve for x, basic alpha there. We did that yesterday. I'll do a scratch work over here and erase it so I can have more room. We know z is equal to x minus mu over sigma multiply z times sigma plus mu. It's going to get us x. This is the formula we need. So I'm going to take the negative 0.99 times my standard deviation of 2,000 and add that to the mean of 30,000. So for Z1, I'll do it in red. We have negative 0.99 times standard deviation of 2,000 plus my mean, 30,000. If I do that in the calculator, it's here, negative 0.99 times 2,000 plus 30,000, 28,020. All right. So this, I don't know if I'm going to write it right there, but that's the lower part. And for Z2, same thing. We have positive 0.99 times multiplication symbol 2,000 plus 30,000. So I'm just going to take my calculator and I'm going to change that negative. I'm just going to do it 31,980. All right. So that's for part A. So they're going to be between 28,020 and 31,980. So that's this part. 95% for part B. The same idea on this one. I didn't show the calculator, did I? So before I move on to this, let's look at the calculator for part A. So we're going to go to, we're looking for a score instead of probability, so we're going to use an inverse model. It's 0.68. Let's see what happens if we use 0.68. And the standard deviation is 2,000. The mean is 30,000. We get this random number here. Huh. Oh wait, we didn't want 0.68. We wanted a 0.84. If we do that, then we get 31,988. And what do we get on here? So let's see, 31,980. So again, a rounding difference on the calculator versus the chart. So as you can see, it gets to be significant once you get to large numbers. That was for Z2. If we do Z1, we do a 0.16 here. 28,011. So right here, that would be this one. So it's pretty close. Again, you can use either the calculator or the charts. For me, it doesn't matter to me. Whatever you're more comfortable with or have access to. So right here, we do the same process. Find out how much is in these little tails here. So 0.025 goes here, and if you add that, that's going to be 0.975 for this one. So I'm just going to use the calculator because this is a good bit of work. And to save time on this video, I'll just say Z1 using the calculator. Hopefully I don't run out of floor space. Is inverse norm of, what do we say it was? 0.025. That's going to give us 26,080. And if we do 0.95 plus 0.025, because we need to add this number right here, we get 33,920. So that was for 0.975 if you wanted to add it up beforehand. Part C, percent tires exceed 26,000. So again, here's 30,000 exceeding 26,000. Would be these guys over here. So for the chart, convert to the Z-score. Uh, 2,000. So I do the math, that's -2 for Z-score. So looking at the chart, -2 for Z-score, 0.0228. That's again for this section right here. Chart always gives area to the left. Don't forget. So to find the area to the right, we're just going to do 1 minus that. Use your calculator. $9,772. How's the percent? minus 7.72%. All right, last question. So we've got 2,000 tires. We want to get how many, kind of like that Oreos problem, would you expect to last more than 28,000? So here's our 30,000. And I already know 28,000, that's one standard deviation to the left. A little mental math. More than. So that's everything over here. So the process would be the same. So this time we use the calculator. It's an old CDF. Lower limit is 28,000. Count your zeros because that's what you mean. Yes, I know. Hopefully I have enough to get to this one video. 1 times, times 10 to the 99. Standard deviation is 2,000, mean is 30,000, 84.13%. So we have 84.13%. Okay. So what I'm going to do with that is I'm going to multiply by the 2,000. Go to mode 1, just do 2,000 times my answer, and I get 1682.7, so let's do 1683. And again, if you use the chart, you will get a slightly different answer. Let me look real quick at the chart. -1 is 0.1587. So 1 minus 0.1587 is that number times 2,000. And it's the same. So 2,000 wasn't a big enough difference to make a different number of tires. Our grading scale, I think it's awesome. Yeah. The grading scale is set up for 1,000 students' test scores. It assumes that the scores are normally distributed with a mean of 75, standard deviation of 15. How many students will have a score between 45 and 75? So again, for time's sake, I'm just going to use a calculator here. So part A, we're between 45 and 75. Our mean is 75. Yeah. We need this probability right here. So using a calculator, meaning I'll pick this one, second bars, on the CDF, 45, 75, 75 for the mean, and what was our standard deviation? 15. That's 2 standard deviations below the mean. 47.72 asks how many students there. Times 1,000. So that's 477 0.2. We can't have 0.2 students. Let's just go for 177. Part B. '60 is the lowest passing score. How many students are expected to pass? Here's 75. Here's 60. We want above 60, or it's 2. Okay, so 60 or above. Let's see, we used this one last time, so let's use Casio this time. Go to your distributions, normal CDF, 60, 1 times 10 to the 99, standard deviation again is 15, and a mean of 75. 8 for 130, oh yeah, that looks familiar. That would be this area in here, and we want to know how many students. There are still 1,000 students. 841 are going to pass, the rest will fail. I'm just going to drop off that 0.3 because, well, we can't have 3/10 of a student. So there's the solution to those homework problems I posted. If you have any questions, feel free to send me an email.